Labguy here. Welcome back, faithful subscribers. Thanks for viewing my videos. I truly appreciate it, and I'm glad you seem to get something out of it. Today we're going to talk about some improvements that I've made to the Cyclops monitor to assist in supporting the development of the Chief, and some discovery I made. I've added a digital voltmeter to the Cyclops so that we can see what the high voltage is that we're running at, so that we can take that into account when examining the scan driving currents and get a general idea of what that relationship is. As you may recall, I've mentioned before, as the beam voltage goes up, the raster will shrink. This is because at higher and higher voltage, the electrons from the electron gun move faster and faster. Well, let's say that the field in the deflection yoke is about this long, where the deflection occurs as the beam goes through. And what happens is that as the electrons go faster, they spend less time inside that zone, and therefore they're deflected less. So the result is, as the high voltage increases on the CRT, the raster will shrink. I'm going to demonstrate that later in this video. The other improvement I've added to the Cyclops is I've added a third control to the two controls that were already there, which were brightness and focus. That's electron beam focus. I've added a third control now. We can adjust the high voltage from 3.5 kilovolts to 9.5 kilovolts. The power supply I used, which is an MCO 4150. It's a very expensive power supply. It has the ability to have its output voltage adjusted from 0 to up to 15,000 volts. Well, early on after I built the Cyclops, I discovered that much over 10 kilovolts, and I started getting arcing problems, and the CRT didn't really like that, though its data sheet says it will tolerate 15,000 volts. The reason for this is that the CRT is the 5AXP4, which was a serviceman's test CRT from the 1960s. The way this worked is a serviceman might come to your house and you have a 21-inch black and white television in a console, huge monster. Rather than lug the entire console back to the shop, he would pull out the television chassis, leaving your CRT behind and the cabinet, and he would take the chassis to the shop and he would stick the 5AXP4 into this chassis. A simple search on YouTube will turn up a video where a fellow does exactly that. Search for 5AXP4 and you'll find several videos about it. Some of them are mine. I will explain in a later video about some of the details that I have to go into about adding the digital voltmeter to the Cyclops project. Because of scaling issues, I built a scaling circuit. I'll cover that in a separate video for you. It's a fascinating topic. It's not as hard as it sounds, and I was startled at how easy it was to do. It took me about an hour to put it all together and make the meter work. At that point, I was adjusting the high voltage power supply with a tweaking tool from behind, and there was a naked circuit board on the back of the Cyclops that my knuckles were pretty close to, and I've raked my knuckles over those contacts a couple of times, and I don't like it. Not a bit. Here's a close-up look of the Cyclops front panel, and I'll quickly go over the features. It has the main on-off knob, which you pull in and out, is also the brightness control. The second knob pulls in and out to it, which is also a secondary off-on switch. and is the focus control, which doesn't do much on a blank raster. There's nothing to see, so you can't tell if it's in focus, out of focus, or whatever. The third knob, with the OCD knob on it, I will buy a matching set of 3 knobs. The Rain Man in me is just going, Argh! The third knob controls the voltage setting of the MCO 4150 high voltage power supply. The little 3-digit voltmeter is indicating the voltage in kilovolts, the actual voltage of the power supply. I'm going to show you that we can adjust that and watch the raster as I change the voltage. First, I'm going to turn the voltage down. As the voltage goes down, the raster grows because the electrons have slowed down. They're spending more time in the deflection region, and therefore they're deflected more and we get a bigger image. It has also gone soft. It is out of focus for sure now. So now let me turn up the high voltage. It's sitting just under 3,000 volts. So we go back up. There's 3,500, 4,000, 5,000 volts, which turns out is where I've been operating. I've been telling you 6 kilovolts, but I'm a liar. I'm just a terrible liar. It was 5,000 volts after all. Going on up, 5,500, 6,000, 6,500, 7,000, 7,500 volts. Turn the brightness down a little. There's more energy in a smaller area now. 8,000 volts. 8,500. 9,000 volts. 9,500. And that's the tops. I put a limiting resistor in the circuit so that we stay under 10 kilovolts and avoid the arcing that I mentioned previously. I like to operate the tube at 5,000 volts. That seems to be a pretty comfortable point where I get a good trade-off for good brightness. We can get really bright if we want, and I get a pretty good deflection. I'm not fighting a high voltage beam to get deflection out of it. So there's one other feature that I've kept secret until just now because I forgot to write it on my script. But for the eagle-eyed among you, I'm going to tell you now. The blanking signal is connected to the grid of the electron gun, and we are blanking off scanning during the blanking intervals. If you thought that raster looked a lot more rectangular than it did last time, you are correct, and you are observant. It is indeed much better looking because we aren't seeing the loopy ends of the lines. It's been cropped out by the blanking signal. So the blanking signal has chopped that lumpy shaped raster that we had before into a much better rectangular structure. I will demonstrate this by unplugging the blanking signal and plugging it in and unplugging it, and you will see the retrace lines appear, because right now during retrace the beam is cut off and we have this beautiful smooth raster of only active scan lines. Blanking on, blanking off. Blanking on, blanking off. Another feature to note the blanking pulse is only 12 volts peak to peak. You may or may not see over on the right side, you can see the blanked out region come up because we've raised the gun's DC level above the threshold that the blanking can turn off to make it visible. This little area over here is the area that's blanked off. The vertical blanking is apparently so stout that it does not appear. So this is representative of the raster that will be in the 2F21 and the 1699 image monoscope tubes, and we are running at 5,000 volts, and we have nearly a 4-inch picture. I think it is a 4-inch picture. And if we start lowering this high voltage down, we're at 3,000 volts there, and that is about the size of the test pattern in that tube. That's actually a bigger scan than that. Don't worry about the vertical offset. The vertical centering control will be repaired. Right now it works just fine, but only moves the raster up and down about 1/10 of an inch. It needs higher current, as well as the scan circuit did. So at the 1,000 volts in the Chief, this raster would be it would be huge, huge. It's going to be huge. I don't know where I heard that. Somebody said that, and I thought it was funny. So there you go. That's the improvements to the Cyclops. Today, I put my current probe on the horizontal deflection, and to my surprise, I got an excellent scan waveform, current waveform on the scope. Looking at the scope, we're now seeing the horizontal drive pulse from the sync generator on the upper trace, and on the bottom trace we are looking at the scan current going to the yoke. This is being picked up with my current probe. The current probe is set for 100 millivolts per amp. The scope is on the 50 millivolt scale, and those pulses are going 2 divisions up and 2 divisions down, which is, somebody help me, about plus and minus an amp of current, or 2 amps peak to peak. And where are those amps coming from, since the power supply is sitting at 75 volts and is drawing less than 10 milliamps? Those amps of current are sloshing back and forth between the inductor and the capacitor, or the condenser if you'd like to think about it as an ignition coil system. The pulse is during the flyback time. That's that sine wave I was talking about that is produced by resonating the inductor and the capacitor. It's a gorgeous sine wave. There is scanning occurring here, but it's hard to see at this scale. I've scaled it so we can see the pulses. So if I increase the gain, we can see that the active scan is just, it's beautifully straight. Beautifully straight. And it's running just about 200 milliamps peak to peak. Beautiful. Once again, I'm going to thank my friend Howie for helping me with this circuit. And I want to apologize to my viewers because I've tried to explain it several times and I almost get it right. Almost. One of these days I'm going to get it right. However, we don't want to get into that mud today. So that's the horizontal scan circuit. As for the vertical scan circuits, I have some ideas for improving the linearity of that system, but I did not get the time to get to that since working on it and showing it to you in the last video. So that pretty much covers the current status of the Chief project, the opportunistic improvements of the Cyclops project, I'll leave you now with a slideshow that will show you the voltmeter and the raster at the same time, with the raster changing size at different voltages. You will be able to read the meter and see the raster. So this is Labguy signing off.